So another pair of conjugate likelihood and prior is normal model. You remember that density function for the normal is, so I'm gonna write it in terms of the likelihood. So y given mu, and I'm gonna skip the constant. It's just exponent minus 1/2, and then you have x minus mu squared divided by sigma. And so if we choose y given mu to be normal, and we assume that sigma squared or sigma is known, and we only need to assume that mu is random, then we need to choose the prior distribution over mu. We need to choose prior distribution over mu that has similar functional form as the likelihood. So we have exponent raised to some power, and then we have mu appears under this power in some squared polynomial. So when we combine those two things together, we can have a second degree polynomial on the exponenta, and it again becomes some distribution that has exponenta minus 1/2, then some second degree polynomial over mu. So we're going to have another normal, and normal happens to be to be the case. So the prior is again exponent minus 1/2, and now it's gonna be mu, and we're gonna assume some mu 0 to be the hyperparameter. That's the mean for our prior value over mu, and then we're gonna have some value tau to be the variance. So in other words, the prior over mu is normal distribution centered at mu 0 and variance tau squared. And so the posterior is just the product of those two exponentes. So the product becomes the difference. And if you do the calculation, you have to do this trick, which is called completing the square. Then you will see that you're going to have another normal on the right-hand side. And those are the parameters of this normal. So the new mu, the posterior mu, is just a linear combination of the y hat, which is the estimated mean from the data, and mu 0. So that's our prior assumption about the value parameter. And so again, you see the situation when we have this shrinkage, when the posterior value for the average here is just a linear combination of the average calculated from the data and the prior assumption about the average value mu. And the variance, the second parameter of this normal distribution, actually here we calculated in terms of precision. So it's n divided by sigma squared. So n divided by the precision of the likelihood plus 1 divided over tau squared. So the precision of the prior. And this term on the right hand side actually gives us not the variance but inverse of the variance, so it gives us the precision for the posterior. So here when we talk about normal model, it's more convenient to talk in terms of the precisions rather than variances, and precision is just 1 over variance. So the variance is just this number flipped. So let's see an example for the normal model. We have SAT results, and the range for SAT score. So it's a standardized test that high school students take. The range for this test, at least for the period when this data was collected, was from 200 to 800. And you have 8 high schools from A to H. And we want to estimate the treatment effect. So different schools were subject to different policy or to different educational program, and we want to understand influence of this policy of the specific educational program on the outcomes of the SAT test for this specific school. So what you see here is estimated values. So those are the averages calculated for each school, and those are some normalized scale. So and then you see the standard error also on this normalized scale. And now we want, so theta j is average effect of coaching program. So it's basically what is the effect of the specific policy on school J, and yj estimates the treatment effect for school J, and standard error is just sigma j. So yj is just calculated from the data. So students take the SAT test, and we calculate how well they did on this SAT test, again on this deviation scale rather than on this 200 to 800 scale. Okay, and two programs appear to work. Program with improvements of 18 and 28. So this is this program A here, and this program G here. So this is program number 1 and program number 7. But there are large standard errors. If you look at the standard errors are 10 and 15. So it looks like there is a huge deviation in the outcomes in those two schools from those calculated averages. And the question is, do the confidence interval overlap? So is there truly treatment effect, or is just due to the observation error? And the classical hypothesis test fails to reject the hypothesis that theta j's are equal. So we stick to this null hypothesis that there are no difference between those two schools. And then if we do the Bayesian analysis, so we start by calculating the pooled estimate and its standard error. So the pooled estimate, basically you calculate average across your averages, and you adjust them, of course, by the variances. So the pool estimate is 7.9. Also, it's not clear what to do with that with this pooled estimate. So now they're really separate estimate. The pool estimate makes much sense. So what we're gonna do Bayes shrinkage. So we will apply a Stein type of estimator. So on the previous slide, we saw two extreme examples of analyzing this data, or two extreme cases. So the first extreme case was to analyze each school separately. And another case was you have this pooled estimation, when every school was pooled together, and then you can probably compare each school separately to this pooled mean. And none of them seems to be sensible. So each school separately, it seems like you're ignoring a lot of the information that's available otherwise. Because you have 8 schools and you only look at one school at a time. So it would be more interesting to look at all of those schools together. But also pooling all of those schools together and just averaging them out also seems pretty strong of an assumption. So we want to find something in the middle. We want to find some approach that allows us to do some pooling, but not complete pooling, when we just average out across all of the schools. And we're going to apply a hierarchical model to do that, and it will allow us to do what is called Bayesian shrinkage. So shrinkage, basically, you can think of fractional pooling. So you pool a little bit from other schools, and you usually have this shrinkage parameter that controls of how much pooling you're doing. And we're going to do a hierarchical model. We're going to assume a normal likelihood. So we're going to assume that this theta parameter here, theta j, is the true treatment effect. And then you observe the actual outcomes, and the outcomes deviate from this true treatment effect, and the deviation is controlled by this variance sigma squared. For each of the school it's different, and we assume it's known. So this is your sampling error. And now we have to specify prior distribution for the unknown parameter theta j, and we are going to assume that theta j is normal. It has the hyperparameters mu and tau squared, and for each of those schools it is the same values of mu and tau squared. And then we're just going to calculate so the prior is the same, the posterior is going to be different because the likelihood will be different. And this is traditional random effect model, has been used in many applications. And now you have this parameter tau that basically tells us how much of variance prior variance you're gonna assume on your parameter theta, the true treatment effect. And this parameter tau basically controls on the scale from each separate school to be estimated separately, or we do complete pooling. And if tau is 0, then we do complete pooling. So it's actually direction in the, so it's in this direction. So it is 0, and this is infinity, so we just reverted the line, but in any case. So when you have tau equals to 0, you basically have a case of complete pooling, and when tau goes to infinity, you have a case of complete separation. And anything in the middle, you have basically some middle case that's what exactly Bayesian shrinkage is. And now, instead of assuming that mu and tau squared are fixed, because we don't really know how much of shrinkage we want to do, we actually going to assume the hyper prior distribution. So we're going to assume distribution, those hyperparameters, and it's proportional to 1 over tau, so it doesn't really depend on the mu. So essentially, we assume that mu is known, and we only have tau squared. So which basically tells us the larger the value of the tau, the more likely you to see this tau. So you want to stay at this, so you want to do, so you put more weight on the pooling rather than on completely separate estimation. And then your Bayesian analysis should actually show you where you should be on this pooling or each school separately estimated scale, okay? And so now it's not your typical normal model, because we have the distribution of the hyperparameters. So essentially what we have here, we have data y, and then data y depends on the parameter theta, and your parameter theta depends on two parameters, mu and tau, tau. And then tau itself is random. So tau itself is random. So it also parameterized with it parameterized with density function. It has no parameters, but it's random itself. So we have to do some inference about that as well. So this tau is random. Okay, so you have 3 layers in your model: hyperparameters mu and tau of your prior model for theta, and then theta defines the likelihood. Okay, so if we write everything together, you have your likelihood, and then you have your prior given the mu and tau parameters, and then you have density for mu and tau. So essentially, this part becomes your prior distribution, right? And so you can do the product, and then you're just going to find out that you're going to have, of course, your likelihood as normals, as the prior is normal and the likelihood is normal, and then you have this distribution of p, mu, and tau, which we know is proportional to 1 over tau. So when you take a product, you have tau to the power -1, and then you take 2 exponents together and combine them. So you don't have this case of conjugacy anymore. So the prior that we have selected does not allow us to calculate analytically the posterior. So we have something that looks like normal, but we have this additive term here that prevents us from doing it analytically. So in this case, we have to do Markov chain Monte Carlo simulations, and we will cover a little bit later in the course how to do those. And now we can do the calculations from MCMC. So essentially, MCMC produces a sample. MCMC produces sample. From tau, mu, and of course, since theta depends on the tau and mu, we can calculate sample over theta. And so what you see here in this main part are the thetas. So those are the main treatment effects. And here you see our hyperparameters mu and tau. And you remember they are the same for each of the schools. And what you see are the quantiles. So we basically take the samples and we calculate the quantiles from the sample. So 2.5% of the samples of theta 1 is going to be below -2, and 97.5% of the observation is going to be below 32. And those are the quantiles at the bottom for mu and tau. And what we can see here now, we remember we were in, let's compare, for example, school A and school G. So those are the schools that seem to be to have the greatest effect, and we were interested in whether they were actually any different or not. So the quantile for the school A is -2 and 32. So that's our 95th interval. And the 95th interval for G is -1 and 27, and we see that the actual overlap, so G is completely inside 1. So our Bayesian analysis tells us that the school A and G are similar. There is no really difference between those two.